Hi, here I have an L298N module. This is a dual H-Brige module which commonly used to drive stepper motors or DC motors. Now the rating of this module is 5 to 35 volts. So here is the ground connection. This is the voltage. Positive voltage comes here, ground connected to here, between 5 to 35 volts. Now, when this jumper wire is there, basically the input voltage will be also connected to this regulator, and the regulator will produce a 5 volts, which that 5 volts will also appear at this pin. And this 5 volt is also supplying power to the chip. In some documents, they suggest that if you want to use more than 12 volts to this pin, you should remove this jumper wire and supply 5 volts from an external power supply. And basically that one goes to the chip. Because the output of this regulator is 5 volts, if we apply much higher voltage to the input, then the efficiency of this regulator would be very small. But anyway, I have tried it. I have applied more than 25 volts to input with this jumper wire connected, and still the regulator could work, and basically you don't need really to apply a 5 volt from external circuit here. Even with this 5 volt, you can supply a small load, like for example an Arduino from here. Okay. Now these are the outputs. So this one goes to one motor, this one goes to another motor. So as I said, this is a dual H-bridge. So one of the H-bridges drive one motor, one of them drive the other motor. These are the freewheeling diodes connected anti-parallel to each switches. When we have an inductive load, if you want to stop that load, an overvoltage will be produced, and this overvoltage can damage the chip. So in order to avoid the overvoltage, we need to use fast diodes. Schottky diodes are preferred, and basically each of them are connected anti-parallel to each switch. So when that overvoltage comes, there is another path for current to flow, so overvoltage will not happen. Okay, so here are the control signals. We have 4 pins available, 2 for one motor, 2 for the other motor, and we have 2 jumper wires, one on the right side and one on the left side. So this right side, when you have this jumper wire there, it's basically you enable the control signals for the right motor, and when we have this one, we enable the control signal for the left H-bridge. Okay, so when we send 5 volts to this pin, then the right motor will turn forward, and if we send 5 volts to the other pin, the right motor will turn backward, and the same way for the other side. So these 2 pins are used to control the right motor, and these 2 pins are used to control the left motor. Even though that this module is rated for 35 volts, these 2 capacitors and the regulators are actually 35 volts rated, the chip itself is rated at 46 volts. So if you want to use the chip alone in another circuit, you can actually go a bit more than 35 volts. Now the chip can handle maximum 4 amps, so 2 amps per each H-bridge. So the continuous current that we can derive from each side is 2 amps. Now temporarily it can go maybe a bit higher, but 2 amps is the maximum continuous current. Okay, so now I'm going to connect this module to power supply, and I will show you what kind of waveform we expect when we send the 5 volt signal to this pin and when we send the 5 volt signal to the other pin. Okay, so I have connected the circuit. So ground is connected to this pin. In this case, 16 volts is connected to the voltage. These are the 2 signal pins, and here I measure the voltage on the oscilloscope using this voltage probe. Now this pin has a voltage of 5 volt with respect to that ground, no matter what voltage I apply. If I apply between 5 volts to 35 volts, because of that regulator, we will get 5 volts on this pin with respect to that ground. Now if I connect this signal pin to the 5 volts, we see that we will get the full DC voltage at the output. Now if I connect the other one, we will get the minus of the DC voltage at the output. This is basically the task of an H-bridge. So if you connect, then the DC voltage will go out. If you connect the opposite polarity, the minus value of the supply voltage will be appeared at the output. Okay, so now I'm going to use Arduino to send pulses to these pins, and we will see what would be the maximum frequency that we can achieve with this module. Okay, so I've connected Arduino to this module. I use the 5-volt pin to directly power Arduino, and we should have common ground. So I connected the ground of Arduino to the ground of that module. Port D2 of Arduino is connected to the signal pin for forward direction of that H-Brige, and port D3 of Arduino is connected to the signal pin for backward direction of that H-Brige. Now, I program Arduino in such a way that we get 10 kilohertz, and as you can see on the oscilloscope, the signal that we have right now is exactly 10 kilohertz with a few hertz deviation. If I change the input voltage, also it will change the output voltage. It's obvious because this voltage is reflected at the output. And if I decrease the voltage below 5 volt, what happens is that the chip will switch off and we will get nothing at the output. One thing to notice is that, okay, let me remove Arduino. So we see that the module itself consumes 5 milliamps. So if you have a setup that gets power directly from the wall, then it's no problem. But if you have a small storage system, then this 5 milliamps is something to consider. And if I now connect the Arduino to this module, you see that the total power consumption is 8 milliamp without connecting anything to the module. Okay, so one thing to notice is that there is a little bit of dead time here. So when we switch two of the switches, we get, for example, this negative voltage. And when we want to switch the positive one, the chip itself has implemented some dead time here to avoid the short circuit between the input and the ground. Now this dead time, you cannot change it. It's internally implemented. Another thing to notice is that we have some kind of disturbance at these points. I think this disturbances is because we have common earth between this oscilloscope and this power supply, and that is causing that sort of disturbance. So in order to demonstrate that this probably is correct, here I have another power supply which does not have earth connection, and I'm going to replace this power supply with that power supply. And we will see whether those disturbances disappear or not. Okay, so now we can see that the disturbances are not there, or at least they are very small. Later on, I plan to use this module to operate a transformer. So I can feed a transformer with this waveform, and then at the output of transformer, I can get different magnitude of voltage. Now, if you want to drive a transformer, one thing to consider is that you want to have exactly the same amount of positive voltage as the negative voltage. Because if this integral is different than that integral, then you have a DC component and that might saturate your transformer. So it's very important to achieve exact same duty cycle positive and negative duty cycle. So this is what I'm going to show you how to achieve it on Arduino. And basically how to get these frequency range very accurately. Okay, so now the setup is clear. I'm going to show you how to code Arduino in such a way that you get exact positive and negative duty cycles. And also we will check what will be the maximum frequency that we can operate this module. All right, so now I will show you how to program this module with Arduino. Now, a while back, I made a video about how to program Arduino in order to achieve very fast pulses in order of 2 megahertz for 50% duty cycle and 4 megahertz for 25% duty cycle. If you haven't watched that video, I suggest that you watch that video first and then come back here. I'll put a link in the description. A bit of advertisement for my own videos. All right, so now let us look at the code. So here basically I declared, let me zoom in. I declared pin number 2 and 3 as output. We have the loop, and then inside the loop I use while loop because we have said that while loop is faster than the main loop. And now here, for example, we can declare pin number 2, let's say as 1, and then we wait for 1 microsecond, and then we then turn it off, and at the same time we turn pin number 3 as on, and then again we wait for 1 microsecond. Now I put 2 clock cycle delay here because when pin number 3 is on, it waits for 1 microsecond, and also it goes back to run this while loop, which is equivalent to 2 clock cycle. So in order to have the positive, let's say, cycle and negative cycle exactly the same duration, so I added these 2 clock cycle delay here. All right, so now if I run this, what do we observe? Nothing. Why nothing? Oh no, something. So we can see that there are some pulses there, but these pulses are a little bit weird because we have now the scales of 400 microseconds. So these pulses are approximately apart 1 millisecond. So this cannot be what we have written here. Those pulses are actually because of the interrupts that happens in Arduino every 1 millisecond. Now let us, for example, increase this value. If I increase this value to 10 microsecond, okay, so let us see what we have now. So of course, now we will have the pulses. Let me zoom out. So this is basically what we have from that H-Brige. So we have some positive voltage, and also we have negative voltage. There is some dead time there between the positive and negative. So here are the dead times, and this is the positive, this is the negative. But as you can see that the signal get interrupted every now and then. These are basically those interrupt pulses that we observed. So if you want to remove that, we have to actually write, for example, no interrupts. If we add this one in the setup section and we run this one again, so those disturbances will disappear because those pulses that were separated 1 millisecond from each other, they will not be there. So this is now a clean signal and we will not have that. So let me I go back to that 1 microsecond. So I disable this interrupt, and then we see that we have those pulses. Um, but when we So those are the pulses because of the interrupt. Now if I enable these, so we don't want any interrupts, so those pulses would disappear. So whenever you are dealing with high frequency application, tens of kilohertz and in those range or higher, then I suggest that we should disable the interrupts. So you see that right now we don't have anything. Okay, so we see that with 1 microsecond delay, actually the board cannot react. So we do not have anything at the output. Now let me I increase it to 3 microsecond. Let's see what do we get. Okay, so even at 3 microsecond, there is some noise there, but still we do not have anything there. So let us go, for example, 4 microsecond. So maybe at 4 microsecond we get something. Yes. So you can see that at 4 microseconds we already have pulses, and you observe that in this case the dead time that we have, these sections are actually almost comparable with the on duration in the reverse direction and on duration in the forward direction. Now, okay, so we have placed 4 microsecond delay and also 4 microsecond um, delay for the other side. So totally the signal should be at least the length of this is 8 microsecond, which means we would expect to get a frequency of 1 over 8 microsecond, which is 125 kilohertz. But now if you look at the frequency that is given on the oscilloscope is 170 kilohertz. Okay, so this one seems that it does not match. What I found out is that you need to add basically 2 delay. In this case, you can find exact frequency that you want. So you add 1 delay here, and also obviously we add another delay there. And in this case, if I run this, what we observe is that the frequency becomes a little bit less because we added some delay, obviously. But it's interesting if you look at the value of the frequency. So the frequency now is 166 point approximately 7 kilohertz. Now, if you use these delays, basically these three and then this one, and you use while loop, in this case, if you put, for example, 4 microsecond delay here and 4 microsecond delay here, the frequency that we will achieve is equal to, you should subtract this one from this one and also one from this one. So we have 3 microsecond here, 3 microsecond there. So we have totally 6 microsecond, and 1 over 6 microsecond gives us 166 kilohertz. This is basically how we can get very accurate frequency only by manipulating these numbers. Let me I bring the calculator here. So yeah, 4 microsecond, 4 microsecond, so 6, each of them minus 1, 3 plus 3 is 6, and if you reverse it, you see 166 kilohertz, 0.6. So it's almost equal here, as you can see in this oscilloscope. Now, for example, let us see based on this logic, if I go 6 microsecond delay here, so we should take 5 microsecond plus 5 microsecond is 10 microseconds. So we should get a frequency of 100 kilohertz. And let us see what do we get. So as you can see, we get a frequency of 100,004 hertz, which is almost 100 kilohertz and 40 hertz, which is very good approximation. So for example, if I put 11, so 10 plus 10 is 20, and 1 over 20 gives you 50 kilohertz. So in this case, you can basically adjust those microsecond range and get the exact value that you want for the frequency of the signal. And one thing to notice is that with this setup, with the setup that we have right now here, we get exactly 50% on and 50% off. Now, if you want to calculate for different frequencies, you have to use if the frequencies cannot be directly given with these microsecond delays. For example, if you want to calculate for 55 kilohertz, let's say, because then you cannot select an exact number here to achieve 55 kilohertz. So 55 kilohertz, let's say what would be the, so this one is equivalent to 18 microsecond and 181 nanosecond. So in order to create 18 microseconds, obviously we need 210 here. Basically, each of them minus 1 is 9, the other one 9, 2 9 is 18. And then we need to create 181 nanosecond delay. But we cannot create 181 nanosecond delay because we have only the resolution of 62.5 nanosecond. So in this case, I add 62.5 here, 62.5 here. So these two together will create 125 nanoseconds. It's not exactly 181, but we will get some frequency very close to 55 kilohertz in this case. Let us see whether my calculation matches the measurement. Yeah, it's almost 55 kilohertz, and okay, there is a little bit more, 190 hertz is more, but that one is because we cannot achieve better resolution here. Okay, so let me I disable these and go back to disable, and here I want to apply 4 microsecond delay, and then obviously we would get a frequency of 166 kilohertz. You observe that the signal right now is a little bit like that way, but if I connect a load to this output, we will have a very nice signal. This is a resistive load that I applied. Now it draws 200 milliamps. Now this signal is a good signal because the integral of positive half cycle is equal to the integral of negative half cycle. So basically we do not have a DC component. So we can safely apply this one to a primary side of a transformer without being worried that we have a DC component which may cause core saturation. We also notice that the on period, the duration of on period in the negative half cycle and duration of on period in the positive half cycle, it's much smaller compared to the dead times here. So this happens at high frequency range. If we decrease the frequency, obviously the on period would be much more than the dead time. So let me now, I decrease the frequency, for example, to 100 kilohertz. So I should put 11 microsecond here. All right, let us see what do we have. Okay, so obviously now we see that the on period is much longer compared to the dead time. So now with this arrangement, we can easily design a transformer. We can select whatever frequency that we want, and basically we can derive a transformer. Now we can also investigate, for example, a comparison between hard switching and soft switching and all those issues, which I'm going to do in other videos. Okay, one last point that I want to mention is that if you have a USB powered oscilloscope, like the one that I have here, and you connect the oscilloscope with the USB cable to your laptop because you want to measure the voltage with it, and at the same time you have an Arduino connected to your laptop with another USB cable because you want to program it and dynamically see the output. In that situation, you cannot measure the output of that H-Brige with this oscilloscope. The reason is that ground of Arduino is connected to the laptop and also ground of oscilloscope is connected to this point. However, at the output of H-Brige, once the positive polarity will be connected to the probe, but then once the positive polarity will be connected to the ground of the probe. So in that case, you actually create a short circuit through your system, a current of few amp will flow through your system, and the signal that you will measure will be completely distorted. So be aware of this error and avoid it. All right, I think this is all for this video. Hope to see you in the next video. Bye.